chemistry. So today we're going to pick up where we left off and talk about molarity, molality, mole fraction, stuff like that. So yesterday we went over percent by mass, percent by volume, molarity, and preparing molar solutions. Today we're going to talk about diluting solutions. So we're going to start on page 467 of your book. So in the lab, you might use concentrated solutions of standard molarities called stock solutions. For example, concentrated hydrochloric acid is 12 molar. That's what you would get if you purchased hydrochloric acid, 12 molar hydrochloric acid. Now recall that a concentrated solution has a large amount of solute. You can prepare a less concentrated solution by diluting the stock solution with solvent. When you add solvent, you increase the number of solvent particles among which the solute particles are moving, which there's a picture of in figure 1514. And thereby decreasing the solution's concentration. Would you still have the same number of moles? Yes, you would, because you're not changing the amount of solute there is. So how do you determine the volume of the stock solution that you must dilute? Well, we know that molarity equals moles of solute divided by liters of solution. You can then rearrange the expression to solve for the moles of solute. Okay, so you've got moles equals molarity times liters. That's just rearranged. Then, because the total number of moles doesn't change, the moles before equals the moles after. Okay, so you can rewrite it as molarity 1 times volume 1 equals molarity 2 times volume 2, because they have an inverse relationship. Your molarity is going to go down as your volume goes up. Okay, so let's do an example. What volume in milliliters of 2 molar calcium chloride stock solution would you use to make 0.5 liters of 0.3 molar calcium chloride solution? Okay, so we are asked for volume. We know that we are given 2 molarity calcium chloride, so that's molar 1 equals 2 mole CaCl2. Then we want a 0.3 molar, so that would be molarity 2. So that's what we have, that's what we want. And we're told that our volume 2 must be 0.5 liters. And so our volume number 1 is unknown. So we know that starting off we have 2 molar, sorry, this is supposed to be a 1. We have 2 molar solution, and we want a 0.3 molar solution in a total of 0.5 liters. So now we can just kind of plug and check. So we use this, we know 2 times V1 equals 0.3 times, and it's asked for, well, we can leave it in liters for now, 0.5. So we end up with 2 V1 equals, where's my calculator? 0.3 times 0.5 should be 0.15. Yeah, that's right. Divided by 2, V1 equals 0.075 liters, because this was liters. So then we convert 0.075 liters times, we want milliliters, so 1,000 milliliters over 1 liter equals 75 milliliters. Okay, so that's all that is. So those are your first 3 problems in your GenoPod. So just use your M1, V1, M2, V2, and you will be good to go. So now let's talk about molality. Okay, so let's keep going down. Okay. Actually, we are going to just erase all of this for now. You can always go back in the video and look at it. Okay, so molality. The volume of a solution changes with temperature as it expands or contracts. This change in volume alters the molarity of the solution. Masses, however, don't change with temperature. So volume can change with temperature, but mass won't. Because of this, it's sometimes more useful to depict solutions in terms of how many moles of solute are dissolved in a specific mass of the solvent. Such a description is called molality, the ratio. Okay, so this is your equation for molality. Molality is used with a lowercase italicized m. Okay. Molality, which is m, equals to your moles of solute over kilograms of solvent. Note again, this is kilograms specifically, so if you have grams, you have to convert it. Come on. There we go. Okay, so let's look at what that would look like if we're calculating molality. So let's say we have 4.5 grams of sodium chloride and 100 grams of water. Calculate the molality. All right, so our solute, we are told, is 4.5 grams of sodium chloride. And our solvent is 100 grams of water. Okay, so that's masses. And mass works for the solvent, but we need moles of solute, so we have to convert. Now, if we add up the molar masses of sodium and chloride, we end up with 58.44, so we can convert 4.5 grams times, let's see, we've got 1 mole NaCl over 58.44 grams, and that gives us 0.077 moles. All right, now we know that this has to be kilograms and that's grams, so we have to convert that down here too. 100 grams times 1 kilogram over 1,000 grams is 0.1 kilogram. Now we have everything we need to plug it into our equation. So molality equals moles, 0.077 over kilograms, 0.1, which gives us 0.77 moles per kilogram, or italicized m. So that's going to be the next two problems in your GenoPad, is you're given the grams of solute and the kilograms of solvent. You first have to convert your grams to moles and your grams to kilograms for the solvent, and then you can just divide to find your molality. Okay, so there's that. And then lastly, we'll talk about mole fractions. So if you know the number of moles of solute and the number of moles of solvent, you can also express the concentration in what's known as a mole fraction, which is your ratio of the number of moles in solute to the total number of moles of the solute and the solvent, which is the solution. So the symbol X is common, like capital X, is commonly used for mole fractions, with the subscripts to indicate the solvent or the solute. Usually the solvent's going to be A and the solute's going to be B. And it can be expressed as followed. Remember, using the lowercase n is going to be number of moles. We learned about that in the gas laws. Okay, so our mole fraction of the solvent equals number of moles of the solvent divided by number of moles of solvent plus number of moles plus solute. Okay? And then it's going to be pretty much the opposite if you want the number of moles of the solute. Okay, so this is A equals solvent, B equals solute. So XB equals NB divided by Na plus NB. Okay? Why must the sum of all mole fractions equal 1? Because in theory, your fraction is kind of like a percent, and you can't have more than 100% of a solution, right? So let's go how that would happen. So let's say hydrochloric acid is in an aqueous solution, so water. For every 100 grams of solution, 37.5 grams are HCl and 62.5 grams will be water. To convert, so, okay. Example. You have HCl. Okay, so for per 100 grams, you have 37.5 grams HCl and 62.5 grams H2O. So now first we have to convert to moles, right? Because everything is always in moles. So if you add up hydrogen and chlorine, 37.5 grams times 1 mole over, that molar mass is going to be 36.5. So that should be just over 1.03 moles of HCl. Then for water, we do the same thing, 62.5 grams times, we know that the molar mass of water at this point is 18.001 or something. So that's going to be 3.47 moles. Now we have all the molar calculations that we need, so we can just plug them in. All right, so our mole fraction of, let's do HCl first, equals the number of moles of HCl, so 1.03 divided by 1.03 plus 3.47, which ends up being, if you do that together, it's just division and addition, ends up being 0.229. And there's no units here because it's moles divided by moles, so your units cancel out. So then, if we were to do the same thing, the mole fraction for water, we just do the opposite. So it's 3.47 divided by 3.47 plus 1.03, which gives us 0.771. Now to double check, because these are our only two things in there, if we did 0.771 plus 0.229, yes, that equals a total of 1, so we're good. So our mole fraction of HCl is 0.229, and our mole fraction of water is 0.771. Okay? So that's how the last two problems for your Junipod. So best of luck, and I will talk to you guys tomorrow. Bye.